Good evening. In today's session, we will be focusing on the topic of spin locks. What is spin lock? A spin lock is a synchronization mechanism used to protect shared resources from concurrent access by multiple threads. The basic idea behind spin lock is if the lock is available, the thread can acquire it and proceed with its critical section. If the lock is not available, the thread keeps spinning in a loop until the lock becomes available. Right? Let us consider this example. Here we are having three threads. These three threads wants to enter into the critical section. Now, before entering into the critical section, all these threads will spin on this particular lock variable. If any thread wants to enter into the critical section, it must and should acquire the lock. So if it is successful in acquiring the lock, it will enter into the critical section. Otherwise, the threads will keep on spinning on that particular lock variable. All right. So all these three threads are trying to contend in for the lock. So all these three threads will spin on this particular variable until it gets the lock. If it is successful, then it will enter into the critical section. Now we'll see the Peterson lock. Peterson lock is a classical software-based mutual exclusion algorithm that allows two threads to share access to a critical section without a race condition. So the lock is named after its creator, Gary Peterson, and it was introduced in 1981. It allows two threads to share the access in a critical section without race condition. So what it will do means it will uses a combination of Boolean flags and integer variable to coordinate the access between the two threads. So the main components of this particular lock is one is Boolean flags and one more is victim. So what are these? Each thread has its own flag. Typically in a two-threaded scenario, if you have a flags for thread 0 and thread 1, if flag of 0 is true, it indicates that thread 0 wants to enter into the critical section. Right? Next, one more variable we are using is victim. The victim variable is used to determine which thread should back off if both the threads wants to enter into the critical section. Peterson lock is effective in preventing starvation in two-threaded scenario by ensuring that at least one of the contending threads will eventually enter into the critical section. However, it's not suitable for scenarios with more than two threads contending for the lock, as it lacks in necessary mechanism to handle the such situations. These are the two problems in this is the main problem in Peterson lock. So it does not handle multiple threads contending for the lock. Here is the code for Peterson lock. These are the first one is the lock function and one was the unlock function. So initially we are using the flag of I equals to true. So flag of I equals to true. This line sets the flag for the current thread I to true, indicating that it wants to enter into the critical section. The thread is expressing its intention to enter the critical section. Next, next line we are having victim equals to I. Here, the victim variable is set the current thread I. The variable is used to determine which thread should back off if both wants access to the critical section. In the next line, while flag of I and victim equals to I. This line indicates a spin loop. The purpose of this loop is to wait until its current threads turn to enter into the critical section. The loop condition checks two things. First one, flag of J. Checks if the other thread J also wants to enter into the critical section. If flag of J is true, it means that other thread is contending. Victim equals to I. Checks if the current thread is victim, meaning it's contended for entering into the critical section. The loop continues spin as long as both the conditions are true, indicating that the other thread is contending, flag of J is true, and the current thread is victim. Victim equals to I. Once the other thread sets flag of J to false, or if the current thread is no longer the victim, the loop exists, and the current thread proceeds to enter into the critical section. And next one, we are having unlock method. In unlock method, we are using flag of I equals to false. This line release the lock by setting the flag for the current thread I to false. This indicates the thread has finished its critical section and is no longer contending for access. This is the simple Peterson lock. Now we'll see the Peterson lock performance based on some simple example. So here we are using one shared variable called count. This particular count is protected by a lock. So if any thread wants to increment this particular count variable, the thread must and should acquire the lock. After acquiring the lock, that particular thread will increment the count variable. So after incrementing the counter variable, that particular thread can release the lock by calling the unlock method, right? So this is a simple one. Now here we are applying the Peterson lock. So for this one, we need to pass two arguments. One is the number of threads, and one more is we need to pass the amount of time we need to run this particular program. So I want to run it for 10 seconds. So when we consider one thread, and if we are running for 10 seconds, then we are getting the throughput 10.19.9 mobs, millions of operations per second. Now let us go with two threads. Now if we consider two threads, the performance is drastically decreasing. So we are getting 2.2 mobs if we consider two threads, right? And one more thing, like if you are trying to use three variables, it won't work. Why? Because it is a two-threaded solution. So here, if you look at the performance for single-threaded performance is better than the two-threaded. So it is not appropriate for multiple threads. Now, in order to avoid this particular two-threaded solution problem, means here it will work for only two threads. If I want to use more than two threads, then it won't work. So to avoid that particular problem, we are going with the next lock called task lock. Task lock is nothing but test and set lock. Test and set lock, here what it will do means, if any thread wants to enter into the critical section, all these threads will spin on this particular lock variable. And after that, whichever thread is succeed in acquiring the lock, that particular thread will enter into the critical section. After entering into the critical section, it will perform its job and it will exit the critical section by releasing the lock. Once that particular lock is released by that particular current thread, remaining threads will again contend for the lock to enter into the critical section. Now we'll see with an example. Now let us consider this case. Here we are having three threads. These three threads will spin on this particular variable. Only one particular thread will succeed in acquiring the lock. That particular thread directly enters into the critical section. And whichever threads are not getting the lock, those threads will keep on spinning on that particular lock variable. And after that, whenever these threads keep on spinning on that particular variable, it causes the contention. After completion of current thread critical section, it will release the lock. Once that particular thread releases the lock, other thread can enter into the critical section. Whichever threads are not getting the lock, those threads will keep on spinning on that particular lock variable, right? So here, whatever the locking is there, the lock is considered in two states, free and taken. So when the lock is free, the value of the Boolean variable is false. And when the lock is taken, the value of the Boolean variable is true. And to acquire the lock, the thread calls the test and set operation. If the result of the test and set operation is false, the thread wins and successfully acquired the lock. If the result is true, the thread loses because another thread has already acquired the lock. And this thread must and should wait, or it should spin on that particular variable. So how to release the lock? So we can simply release the lock by writing false. So here it is simple. So if any thread wants to acquire the lock, it performs test operation, test and set operation. If the result is false, then it acquires the lock, it will enter into the critical section. If the result is true, indicating that some thread is already in the critical section, so it has to wait. This is the code for implementing the task lock. Here we are using atomic Boolean state equals to new atomic Boolean false. Here lock state is a atomic Boolean. This line declares an atomic variable named state and initialize it with false. Next, while state dot get and set of true. This line begins with a declaration of lock method, while state dot get and set of true. This line is the core of the lock method. State dot get and set is true. Automatically reads the current value of the state and sets it to true. The while loop continues to spin as long as the original value was true. The purpose of this particular loop is to keep spinning until the lock is successfully acquired. If the particular thread is not if that particular thread is failed in acquiring the lock, then it will keep on spinning on this particular while loop until it succeeds. Next, we are using the unlock method. In unlock method, a state dot set false. This line automatically sets the value of the state to false. It releases the lock, indicating that it is now free and available other threads to acquire. Next, problems with task lock, test and set lock. So here, task lock invalidates cache line. When a thread acquires or releases the lock using task, test and set atomic operation, it often involves writing a shared memory location. In a multi-core or multi-processor system, each core or processor may have its own cache. When one or more updates memory location, it may cause the invalidation of the corresponding cache line in other cores, leading to cache coherence issues. This when invalidation, whatever this particular task invalidates cache lines, this invalidation can result in cache miss and consequently additional overhead due to the need to fetch the updated data from the main memory. Next problem is spinners, machine cache, and go to bus. In the context of spin locks are spinning while waiting for the lock to become available. The threads continuously checks the status of the state variable in loop. If the variable is frequently updated by other threads, it can lead to the cache misses, as the local cache needs to be updated with the most recent values from the main memory. So frequent cache misses can result in increased bus traffic and contention, in fact, the overall performance of the system. Next, if any thread wants to release the lock, delayed behind spinners means when a thread wants to release a lock, it may face delays if other threads are actively spinning and accessing the same memory location. The releasing thread might be delayed behind the spinner's threads due to the cache coherent issues and need for synchronization. These are the problems with the task lock. Now we'll see one example program. Now we are using the same counter variable example only. Now we'll update the lock to task lock. And we are passing number of threads is 1, and I want to run it for 10 seconds. If we consider one thread, and if we are running for 10 seconds, we are getting the throughput 20.07 MOPS, millions of operations per second. When we compared with Peterson lock, for Peterson lock, we are getting the throughput 19.9 MOPS. So like if we are using the task lock, we are getting a better performance. Now, instead of a single thread, let us consider two threads. And for two threads, we're getting the performance or throughput 5.9 MOPS, so which is better than the Peterson lock. Now let us consider four threads. And for four threads, we're getting a throughput 2.4 MOPS. Next, let us go with eight threads. For 8 threads, we are getting throughput of 1.4 MOPS. So whenever we are increasing the number of threads, the performance is decreasing because of the contention. Why? Because whenever one thread acquired the lock, then other threads will keep on spinning on that particular lock variable, which causes the contention. So because of that contention, the performance is decreasing. Right now, in order to avoid this particular problem, next we are going with the next lock called test and set lock. Now, in test and set lock, we are overcoming the problem of task lock. In task lock, what we are doing is, like, if any thread wants to enter into the critical section, it acquires the lock. Remaining threads will keep on spinning on that particular loop, which leads to the contention. So to avoid that particular problem, so here what we are doing is, in test and set lock, threads first read the lock state, sorry, and it keep on spinning on that particular local copy of that particular lock variable status, right? So previously, every thread will keep on spinning on that particular loop, which, on that particular lock variable, which causes the contention. So to avoid that, in t-task, what we are doing is, each thread go to the lock variable and read its status, and it will get the cache copy, and it will spin on that particular cache location only. Means it will spin, it is a local spin. And once the lock is busy, those threads will keep on spinning in its own location. Whenever lock is available, all the waiting threads will keep on spinning on that particular variable once again, which leads to the contention. But when compared to the task lock, whatever, instead of continuously spinning on that particular variable, so we are reducing that amount of time in t-task lock. So then whichever thread is succeed in acquiring the lock, that particular thread will enter into the critical section and release the lock. So here, what is the different approach? What is the difference between the task and t-task is, t-task continuously spins, all the threads will spinning on that particular lock variable. But when it comes to the t-task, the threads will check the lock status. If the lock is free, then only those threads will contend for the lock. Otherwise, these threads will spin on its own cache location or its own local. It will perform local spinning. Now, whatever the task lock is there, so task lock implemented in 2 stages. One is looking stage and one more is pouncing stage. First one is looking stage. So looking stage in the sense, wait until the lock looks free. During the looking phase, a thread is waiting until it perceives the lock. During the lurking stage, a thread is waiting until it perceives the lock is available or looks free. This typically involves repeatedly reading the state of the lock. The thread continues to wait in this stage until the read operation indicates that the lock is potentially free. Spin while read returns true. Once the thread observes that the lock looks taken, it enters into a spin loop. The spinning loop continues as long as thread operation indicates that the lock is still taken. The purpose of this spinning loop is to actively wait for the lock to become available with the expectation that the lock will be released soon. Next, as long as the lock looks available, when thread reads as soon as the lock looks available, when the thread operation finally returns false, indicating that the lock is potentially free, and the thread transitions to the pouncing stage. Pouncing state. At this point, the thread believes that the lock is available and attempts to acquire it. Read returns false, indicating that the thread checks the read operation indeed returns false, confirming that the lock is free. The thread then proceeds to call the test and set task operation to attempt to acquire the lock automatically. Call task to acquire lock. If the task operation is successful, like when it will be successful, if it returns true, the thread has successfully acquired the lock and can proceed to the critical section. If the task operation is not successful, at that time it will return false. It indicating that another thread acquired the lock just before the current thread transitions back to the lurking stage to wait for another opportunity. Right? This is simple. So first it will wait until the lock looks free. Once it looks free, then it will keep on spinning on that particular variable. So as soon as the lock is available, if return is false, it indicating that lock is free, then it directly calls the task operation to acquire the lock. If it is successful, it will enter into the critical section. Otherwise, it will release the lock. It will go back to the lurking phase. Here is the code for test and set lock. So here, this is similar to the test and set lock. One statement we are adding here is this particular while loop, while state dot get. So here, while state dot get, wait until lock looks free. And whatever this particular state while wait until the lock looks free is, so instead of continuously spinning on that particular state variable, here what we are doing is this one repeatedly checking the state of the lock, either by directly accessing a shared variable or using an atomic operation. Now here, while state dot get, this is an inner loop that spins while the state is true, indicating that the lock is currently taken by another thread. So if the state dot get is true, it will keep on spinning on that particular while loop until it becomes false. So when it will be false, when the lock is released, then it will be false, so that the other threads can contend for the lock. Next, then try to acquire it. So once we are waiting till state dot get is false. So once it is false, we'll exit from that particular wait loop. Then we are performing the state dot get and set of true. So if it is succeed, then that particular thread will enter into the critical section. If it is failure, again it will go back and it will be waiting in the wait loop. Next, wait until lock looks free. And one more is spin on local cache and no bus use while the lock is busy. So these are the advantages with the test and set lock. So previously, what will happen in task lock? In task lock, we are continuous. If a particular thread is failed in acquiring the lock, that particular thread will keep on spinning on that particular state variable or lock variable, which causes the contention. But here, that particular problem we are overcoming by using the new concept called instead of continuously spinning, we are waiting until the lock looks free. So if the lock is free, then we are trying to contend for the lock. So here, one of the advantages, we are spinning on the local cache memories. and no bus used while the lock is busy. So those are the advantages with the test test and set lock. Next, problem. So here, what is the problem is invalidation storm. Means how invalidation storm is happening. When the particular thread releases the lock, whichever the threads trying to acquire the locks, so all those whichever threads are trying to acquire the lock, all those threads are trying to perform the get and set operation or test and set operation on that particular variable, which causes the invalidation storm. Means the release of the lock may lead to an invalidation storm when the cached value of the lock in other threads become invalid. As each thread reads the now invalid value from its local cache, it may result in multiple cache misses, causing the surge of the bus traffic as threads update caches with the current value from the main memory. This is causing the cache invalidation. All right. Or now we'll consider same example and we'll check the performance of t-test lock. Sorry. So we need to pass the arguments. Like here we are passing one thread and I want to run it for 10 seconds. And we are getting the throughput around 18.4 MOPS. Now let us consider two threads. For two threads, we're getting performance 5.5 MOPS. Four threads. 2.5 7 MOPS. 8 threads and we are running for 10 seconds. And we are getting the performance 1.5 MOPS. Right. So if you look at the throughput of task log and t-task log, t-task log performance is getting better whenever number of threads is increasing. Means it is handling the contention. So if you look at the performance of task log, in task log for single thread, two threads were getting better performance. When the number of threads is increasing, means when if you look at the number of threads is 4 and 8, and we are comparing that particular performance with the t-task log. For t-task, we are getting the for 4 threads, we're getting 2.5 MOPS, and for 8 threads, we're getting 1.5 MOPS. Means whenever the contention is more, at that time, t-task lock is performing better than the task lock. Right? Next. T-task lock is performing better than the task lock means it handles the contention effectively. But the main problem with task lock, T-task lock is whenever the particular lock, a particular thread releases the lock, all the threads are trying to get the lock, which causes the contention. So to avoid that particular contention, we are going with the one more lock called, like we are going the one more approach. So here, what is the approach is, we are checking that whether the lock is free or not. So if the lock looks free, but if it is failed to get, then what we are doing means there must be a contention. So then we are performing the back off. So back off use it to avoid the collisions. Now the approach is next lock is exponential back off. So what is the approach is, if a particular thread is failed in acquiring the lock, that particular thread will be wait for random duration before it retries to acquire the lock. So whenever that particular particular thread is failed to acquire the lock, we are doubles the expected wait. That is approach. So each thread will try to acquire the lock. If it is successful, it will enter into the critical section. If it is failure, so then we are sending that particular thread to waiting period, waiting period, or wait period, or we can sometimes we can send it to the sleep mode also. We can send it to sleep, or we can send it to the wait, or wait in the sense that particular thread will not perform any operation. Simply it will be idle. So after that wait period completes, it try to acquire the lock one more time. If it is failure, then doubles the expected wait. So that whatever the in task lock, whenever the lock is released, then all the threads are trying to perform the get and set operation, which leads to the contention or cache invalidation. So that in order to avoid that, we are using the random waiting period. So whenever thread is successful in acquiring lock, it will enter into the critical. If it is failure, we are sending that particular thread to random waiting period. All right. So this is the advantage with this particular lock. So whatever the contention is there, so effectively is handled in exponential back of lock. Here is the code for exponential back of lock. So remaining code is similar to the T-task lock only, except these last two lines. Like one is sleep random modulus delay, and one was if condition. Right. So here a random is a function which generates a random number, and then a modulus delay, which returns the remainder of the division of the left operand by the right operand. What sleep? Sleep is a function that causes the current thread to sleep for a specific period. So here, how we are specifying that particular specific period means random. So here, why we are using the random? Because if I'm giving the delay, whenever all the threads are trying to contend for the lock, if we are providing the same delay to each and every thread, again, all the threads after that particular delay time, every thread will try to contend for the lock, which causes the contention. So to avoid that contention, so what we are doing here is we are adding the randomness to that particular delay, so that threads will contend for the lock in different times, right? So that we are doing. So simply this particular sleep random modulus delay generates a random number, takes its modulus with the current delay, and then sleeps for the result. This introduces randomness to the sleep duration. Next line, if delay less than max delay. So this line checks whether the current delay is less than the maximum delay. So the purpose of this check is to ensure that the delay does not exceed a certain threshold. So we need to specify the minimum delay and maximum delay. Based on that, we'll check that condition. Next line. Delay equals to 2 into delay. So if the current delay is less than the max delay, this line doubles the delay for the next iteration. So the intention is to gradually increase the delay in an exponential manner, as is common in exponential strategies. Right. So when compared to the task lock or T task lock, so whatever the contention is there, it is effectively handling in exponential back-off lock. So what is the good in this? So good is easy to implement. So it beats the performance of T task lock when the contention is more. And what is the bad about this particular lock? Or what is the disadvantage of exponential back-off? First one is when it comes to the parameters, minimum delay and maximum delay, we must and should choose parameters carefully. So if the parameters is not appropriate, then sometimes it leads to the drastical performance changes. And one more is it is not portable across all the platforms. So it will support only certain platforms only. But here, if you look at the exponential back-off lock, when compared to the task lock, T-task improves the contention, like it handles the contention effectively. And when compared to the T-task lock, exponential back-off lock, still it will effectively handles the contention. But here, when it comes to the contention, but it is not up to the mark. So in order to avoid this particular contention, we need to go with a different approach. And one more is here, all these locks, Peterson lock, like task lock, T-task lock, and exponential backoff is not following the fifth order. Fifth order FCFS order, first come first serve order, right? So here sometimes these it may cause the starvation. So to avoid that particular problem, we are going with the concept of Q locks. Now, let's consider some example to see the results of exponential backoff. So we are using the backoff lock. So initially we are consuming one thread and I want to run it for 10 seconds. When we consider one thread and if we are running for 10 seconds, we're getting 18.5 mobs throughput. Now let us go with the two threads. For two threads, we're getting performance 18.51. Let us go with for four threads, we're getting 17.53 mobs. Let us go with 8. And for number of threads 8 and the duration is 10 seconds, we're getting 9.3 mobs throughput. Now, if you look at the performance when compared to the T-task lock, every time, like if we are considering one thread or two threads or four threads, or 8 threads, exponential backoff is giving the better performance or better throughput. Now here, why it is giving the better throughput? One main advantage here with exponential backoff is it handles the contention in effective manner. All right. So here, if you look at the task log, in task log, what we are doing in task log, if any thread wants to enter into the critical section, all the threads will be trying to acquire the lock variable. If whichever thread is succeed in acquiring the lock, that particular thread will enter into the critical section. Remaining threads will keep on spinning on that particular lock variable, which causes the contention. So in order to avoid that particular problem, instead of continuously spinning on that particular lock variable, so just we are reading the state value. If the state is free, then that particular thread will be contending for the lock. This is the approach which we are using in t-task lock, right? But still, when the lock is free, all the threads are trying to acquire the lock, which causes the contention, right? So in order to avoid that particular problem, in exponential backoff, what we're doing is like initially all the threads will check the state value. If the state lock is free, then the particular thread will acquire the lock and enter its critical section. Remaining threads, whichever threads failed in acquiring the lock, that particular those threads will spin. Instead of spinning on that particular lock variable, it will check. If it is failure, then we are introducing the backoff concept. Backoff means we are sending that particular thread for some random amount of waiting time. So once that waiting time is completed, then again that particular thread will contend for the lock. So if it is again failed, then we are doubles the waiting period. So every time if we are doing this particular thing, then that particular lock means handles the contention effectively. So because of this particular changes made the exponential backoff better lock, right? But still, this particular exponential backoff lock lags in FCFS. So threads like sometimes high priority thread comes, whichever the lower priority threads will be in the waiting state only. So which leads to the starvation. So that is a one problem. So and one more is still there is a contention. Why? Because when the lock is released or whenever the random period is slightly less, then it may cause the contention. So we need to choose the parameters in an effective manner, and it is not portable across all the platforms. So to avoid these problems, in the next section, we are going to discuss about Q locks. Thank you.